Hello, CKVK Seminar. My name is Michael Klug, and I'm going to talk a little bit about some Z2 invariants that are found throughout low-dimensional topology and their relationships with one another. I'd like to start by thanking the organizers and just mentioning that my father and grandfather both went to Ohio State, and Buckeyes games were always a large part of my childhood, an important everyday ritual. So I'm excited to be giving a talk that's in some sense associated with Ohio State. Okay. So my talk is titled A Relative Version of Rocklin's Theorem. I'll show you which Rocklin's theorem I mean in a moment here. My name is Michael Klug. I'm a final year PhD student at UC-Berkeley and the Max Planck Institute for Mathematik at Bonn in Germany. Rob Kirby is my advisor at Berkeley, and Peter Teichner is my advisor at the Max Planck Institute. So I'm going to give this talk on all these different Z2 invariants, and it's going to kind of have this invariantology flavor to it, where it's really this relationship between the invariants that I'm interested in discussing. So there will be a bunch of different invariants, probably many of which you've seen before, and then a relationship between them, hopefully that you haven't seen before. So I'm going to start by just flashing a theorem, a classical theorem of Rocklin at you. And I'm not necessarily expecting you to know all these things are. Then I'll show you this relative version of it, and I'm not going to have explained what any of the terms are yet. I'm just trying to give you some orientation for where we're going. And then I will circle back and actually discuss what all of these different invariants are. And then we'll put them all together and get some nice theorems. And then we'll discuss several generalizations of this, where we weaken the hypotheses quite a bit. So I'm going to start by just flashing these theorems at you. So here is what I'm calling Rocklin's theorem, although it has a long history in the version that I have written here, so that with other names being Curvaire and Milner having written a paper on this in a special case. Matsumoto wrote a very nice paper giving a different flavored proof of this. Rocklin originally discovered this and proved it, and then Kirby and Friedman proved a topological variant of this, which I'll be very lightly discussing throughout. But we'll also be using the topological, our results will extend to the topological case fairly readily, actually, given this version for the closed form manifold. So the hypothesis is that you have a closed-oriented form manifold. You might as well, if you only like smooth ones, just assume smooth throughout the whole talk, and these Kirby-Siebenmann invariants will just vanish. If you like, this is actually a definition of the Kirby-Siebenmann invariant, kind of combinatorial definition. And also, we'll have this condition that the first homology of X with integral coefficients vanishes. Although this condition can be defined away, and I'll mention later what I mean. So this theorem is actually true verbatim, erasing that condition. You just have to change your definitions a little bit. And let F be an orientable characteristic surface in X. So I'll explain what I mean by characteristic in a little bit. Then we have this formula here. So on the left-hand side, there's what is called the Arf invariant of F. So there's going to be a few Arf invariants in this talk, and this will be one of them. And I'll discuss what that actually is in a little bit here. And on the right-hand side, you have the signature of the form manifold, the self-intersection of the surface, and then it's just a general algebra fact that about integral unimodular lattices, that if you look at the signature minus the square of a characteristic element, it's always divisible by 8. So you can divide out by 8. And this theorem says that this theorem gives you this equality. If you care about the topological case, you add on Kirby-Siebenmann. And our aim will be to discuss a certain generalization of this, where X is allowed to have boundary and where F is properly embedded in X. And the case we'll start with is leaving these orientability conditions, and we'll insist that F have connected boundary. So this is where we're going. So the hypothesis will be that X is a compact-oriented four manifold with integral homology sphere boundary, and F is a properly embedded oriented surface in X with a connected boundary. And then we have two extra terms in the previous equation, two boundary terms. So in this equation, we'll have the Arf invariant, this four-dimensional one. The first one that appears here is the Arf invariant of a characteristic surface. The second one is the Arf invariant of a knot in a homology sphere. And the other term over here, you could call it the Arf invariant of the homology sphere, but it's traditionally denoted mu of a homology sphere, or it's called the Rocklin invariant of a homology sphere. So these are kind of all of the Z mod 2 invariants, or a lot of the Z mod 2 invariants, all in one nice equation. So if there's any one of them that you don't like, you can take this as the definition of it by putting all the other ones on the other side. Or a fun way of computing it. So this tells you, for example, how to compute the Arf invariant given this very general four-dimensional thing bounding it. So now I'm going to circle back and we'll start from the beginning. This is just to show you the invariantology stuff that we're going to be doing, all the different invariants that will be involved. So our plan is that I'm going to first explain to you this Arf invariant of a characteristic surface in a four manifold, the Arf invariant of a knot in a homology sphere, and the Rocklin invariant of a homology sphere. And how we'll go about doing this is I'll start with a little bit of algebra just involving Arf invariants. Then I'll discuss some three-dimensional knot theory. Then I'll discuss characteristic surfaces in four manifolds. We'll briefly mention this lemma that bridges three-dimensional and four-dimensional techniques. So it gives you a four-dimensional method of computing this three-dimensional Arf invariant of a knot. And then we'll put those together, and it'll, together with this first theorem I showed you, this closed case, it'll quickly yield the relative case. And after we do that, I'll give you a more impressionistic view of how to generalize some of these things. So in particular, you don't need to insist that the boundary of F be a link, but when you try and, be a knot, it can be a link, but when you try and make this generalization, you're led to this condition of properness on your link. You also don't need to insist that F be orientable, and when you drop the hypothesis that F be orientable, you're led instead of Arf invariants to so-called Brown invariants. And if you're in the know with these things, whenever you hear Arf invariants, you're thinking that there's spin structures in the background. And when you hear Brown invariants, it means there's pin structures, or more specifically, pin minus structures in the background. And so when you can in fact generalize this whole theorem to allow X to just be an arbitrary four manifold, compact orientable four manifold, with in fact arbitrary three manifold boundary. And you can generalize this formula also there, and there you're led to thinking a bit about pin structures. And to get there, or my way of getting to that general formula was to first prove these warm-up cases and then understand them in terms of spin structures and in terms of pin structures, and then that was enough warm-up. We get to the final theorem. So I'll just show that theorem at the end without even really explaining what it entails, but I'll be putting all this, I've written this in a paper, and I'll be putting it on the archive in a few weeks. That's where you can find this stuff. Okay, so let me talk a little bit about just the algebra involved with the Arf invariant. So the setup is that V is a finite dimensional Z2 vector space, and we're given some non-degenerate symmetric form on it. And we'll call maps Q from the vector space V to Z mod 2 that satisfy this condition here. So they're not homomorphisms, but they're almost homomorphisms up to this factor involving the intersection form. These are called quadratic enhancements of the intersection form, or of the bilinear form that we're given. And they in fact determine the bilinear form, but usually the setup we'll see is that we're given V, we're given this bilinear form, and then we look at different quadratic enhancements of them. And when you have this V together with this quadratic enhancement, there's a Z2 invariant that actually completely classifies this space, vector space together with a quadratic enhancement called the Arf invariant. And it's in fact in this algebraic setting that Arf first discovered the Arf invariant. And one simple definition of it, the one that will later generalize, so that you might usually see a definition in terms of a certain symplectic basis for V, which always exists when you're in this setting. But the definition I'll give is the so-called democratic definition. So Q takes on values 0 and 1, and it turns out that it will always take one value more often than the other. You have to prove this, but it'll never be the case where it takes 0 and 1 the same number of times. And so the value Arf is just which of those two values gets more votes, so-called democratic invariant. Okay, so now I'm going to tell you about how this Arf invariant, this little bit of algebra, appears in 3 dimensions and then 4 dimensions. And we'll put it together. The first 3 dimensions, you have the Arf invariant in 3-dimensional knot theory. So the setup is that I'm given a knot in an integral homology sphere, an oriented integral homology sphere. And I'm going to define for you a Z mod 2 valued invariant of this knot. It's in fact a concordance invariant. So it's the sort of simplest slice obstruction when you just do this in S3. So what you do to define this is you first make a choice and then you show that it doesn't matter. So the choice is the choice of Seifert surface for K. So S will be our Seifert surface. And then our vector space is this first homology of S with Z2 coefficients. And our bilinear form is the intersection form on S, which since we have a knot and not a link, this is indeed non-degenerate. And then our quadratic enhancement is this Q here takes an element of homology, it realizes it as an embedded circle on the Seifert surface, and then it computes the linking number of that circle together with a positive push-off of that circle, or negative, because you're just taking it mod 2 here. Then you'd have to check. The first thing to check is that this is well-defined, independent of how you represent C. And the second thing is that it's actually a quadratic enhancement of the intersection form. And then you can define the Arf invariant of this Q, but then you should check, to check it only depends on the knot, you should check that it actually is invariant of the choice of Seifert surface. And one method for doing that is that any 2 Seifert surfaces for a fixed knot in a homology sphere are related by so-called S equivalents. So you can change a Seifert surface by adding a tube that comes off and comes back on the same side of the Seifert surface to preserve orientability, removing such a tube, snipping it along a compressing disk, or just isotoping your surface. And in fact, those moves suffice to get between any 2 Seifert surfaces. And therefore, you just have to check that adding a tube doesn't change this Arf invariant. And so that's something I leave to you. But this gives you this nice C mod 2 invariant of knots. You can compute it, for example, for the trefoil in S3, if you'd like an example. So now I'm going to give you another occurrence of the Arf invariant in low-dimensional topology, namely characteristic surfaces in 4 manifolds. So first, let me tell you what a characteristic surface is. So our setup for now will be that X is a closed-oriented compact 4 manifold with 0 first integral homology, and F is an orientable surface embedded in X. And then we call F characteristic. Well, one definition is just that the homology class is dual to the second Stiefel-Whitney class of X, or equivalently, that whenever you take any homology class, G, any second homology class, and you look at its self-intersection number, so you can maybe realize G by a surface, and you can count how many times it intersects itself when you push off itself, or you can look at the normal Euler number, the Euler class of the normal bundle. So that's this quantity on the right here, G intersect G, and on the left, it's F intersect G. And these are always equal mod 2. So in some sense, these are very special homology classes. It means that F, at least mod 2, F really spreads out throughout your whole manifold and understands the other homology classes, at least mod 2. Although that intuition isn't so good if, for example, you're in an even simply connected form manifold where you can have a lot of homology, but this F can just be anything. But anyhow, for example, CP1 inside of CP2 is a characteristic homology class, but 2 times CP1 is not a characteristic homology class. And when you have a characteristic surface, then you can get this quadratic refinement of the intersection form. And it's defined by taking an element of first homology of your surface, and you again represent that by an embedded curve on F. Here, this is denoted by partial D. And then you let D be an orientable surface that bounds this curve in your form manifold. And if you like, you can assume this D is a framed D. When you're looking for example, looking for compression disks of a surface in a form manifold, you always have to worry. You have a curve you'd like to compress along. You have to find an embedded disk. It has to be disjoint from your original surface, and it has to be framed. There's a Z worth of framing issues. And so you can always arrange to have things framed, but this will introduce more self-intersections. So if you're unfamiliar with the framing, that's why it's in orange. You can just kind of forget it. But this takes X to D intersect F plus this framing. And the fact that F is characteristic is very important in showing why this is well defined. For example, if you change D by if there was some other homology class, just disjoint from F, then you could just tube D into that homology class. And so to get this well defined, you very much need F to be characteristic. And then you get this Arf invariant, which in the closed case actually only depends on the homology class of F. And then Rocklin proved this theorem, that the Arf invariant of F is related to these quantities. So the signature of X minus the self-intersection form. So this is the first formula I showed you in a simplified form, but it's just Rocklin's version of it. And a little history, the special case where X is spin. So where X is spin, you can take F to just be the trivial homology class, just a little, say, sphere in a 4-ball in your form manifold. And what happens here is the Arf invariant of the sphere is just defined to be 0. The self-intersection is 0. And so what you get is this signature divided by 8 is 0 mod 2. Or said differently, 16 divides the signature. So it's 1 more factor than you'd expect. This is the original Rocklin's theorem. Another special case is just when F can be represented by a 2-sphere. This is in this very nice paper of Kerver and Milner. They look at this special case, and they derive this formula in this special case. Okay. So one consequence of Rocklin's theorem is you get this Arf invariant of an integral homology sphere, sort of, or a Z2 invariant. So what you do is you take your integral homology sphere, sigma here, and you choose some spin bounding, or you could say simply connected an even bounding form manifold. And then you take the signature of this form manifold and you divide it by 8, and you look at that mod 2. And if we look back to this preceding theorem of Rocklin, this shows that this is well defined, independent of the choice of form manifold. And so you get this Z2 invariant of your integral homology sphere. Or more generally, this is parenthetical remark at the bottom here, more generally, if you have a 3-manifold, compact 3-manifold together with a spin structure on that 3-manifold, then you get a Z mod 16 valued invariant, which is called the mu invariant of that by taking a signature of a bounding form manifold. So, which we'll see that just at the very end. I just mentioned that here because in this final generalization of this relative Rocklin theorem, this term will appear. And we'll see the powers of 2 get larger as we go through the talks. We start with all these just Z mod 2s, and then when we want to deal with non-orientable things, there's going to be some Z mod 4s and some Z mod 8s and some Z mod 16s. So we'll see that a little bit more. this is this lemma connecting 3 and 4 dimensions that's relevant for the proof of this relative Rocklin theorem that I showed you, that we're about to prove here. So this lemma tells you that there's a 3-dimensional quantity, the Arf invariant of a knot. So K is a knot in an integral homology sphere. And on the right of this equation here, we have its Arf invariant. And this lemma is telling you there's a 4-dimensional way of computing it. Namely, you look at any connected orientable surface in this homology sphere cross I with boundary that knot. And it turns out that you can write down the same quadratic refinement of the intersection form of F that we wrote down in the closed case a few slides ago. So this works because F has connected boundary, and that's actually fairly fundamental. And F is indeed characteristic in sigma cross I. There's no interesting second homology because sigma is a homology sphere. And you can compute the Arf invariant, the 4-dimensional Arf invariant of that surface F. And that 4-dimensional Arf invariant will equal the 3-dimensional Arf invariant of its boundary. So the proof of this is not terribly difficult. Once you have all your invariants established and they're all well-defined, then a lot of these proofs are fairly easy because you can, since everything's well-defined and it usually depends on a choice, you can choose the nicest possible thing. So here, it turns out that this Arf of F, it only depends on the boundary of F. If you want to change the actual F, you can add tubes to it to change the F while leaving the boundary fixed. And these will all have the same Arf invariant. It's kind of like in the closed case, how it only depended on the homology class. Or in the 3-dimensional case, how it didn't depend on the Seifert surface. And so you first check that, and in fact, it only depends on the cobordism class of the boundary, although we won't be using that. But that just means you can add a little cobordism, a little annulus, and that's away from all the topology of F, so that wouldn't change this left-hand term over here. And so you can just compute Arf of F by choosing any surface with its boundary. And in particular, you can choose the Seifert surface for the boundary and just push it into sigma cross I. And then you have to check. So this boils it all down to a little check that the Q of that Seifert surface is equal to the Q of this surface F. So they in fact have equal quadratic refinements, and so their Arf invariants are equal. So this is, if you like, a 4-dimensional way of computing the Arf invariant. Okay, so now we're ready to start putting together some of these things. So this was this theorem from the very beginning. So X is a compact-oriented form manifold with integral homology sphere boundary. And for now, it has 0 first homology. And F is an orientable characteristic surface properly embedded in X with a connected boundary. And now we have 2 Arf invariants. So the first Arf invariant is a 4-dimensional Arf invariant of your surface. The second Arf invariant is a 3-dimensional Arf invariant of a knot in a homology sphere with the familiar signature and self-intersection number. I should mention this self-intersection here is computed by taking the 0 push-off on the boundary and extending it over F. And then we have this Rocklin invariant of the boundary, and we have this Kirby-Siebenmann invariant in the event that we're in a topological form manifold that isn't smoothable. So all these nice C2 invariants in one place. So the proof of this, it implies the closed case, but it also follows from the closed case without too much extra effort. So what I'm going to do is I'm going to close up, I have this form manifold with boundary. I'm going to cap off the boundary with a nice spin form manifold. That'll introduce this Rocklin term. And I'm going to take the surface and I'm going to cap it off also inside that same form manifold. And that'll contribute to this extra Arf term here. So it's not too tricky. So let me show you how that goes. So here's a schematic of what I was just mentioning. So you can start by looking at the black here. This is the form manifold X, and F is the characteristic surface. So what you can first do is to get a closed surface, you can take just a little color of the boundary and extend this form manifold by adding just a little sigma cross I to the top. And you can take a Seifert surface bounding your knot. Remember, your boundary of F is in the boundary of X, which is a homology sphere. So it has a Seifert surface, and you can just push that in to this color neighborhood, if you like. Then you get, that's this green surface here, F of W. And F together with F of W is now a closed form manifold, closed surface. To get a closed form manifold, you can take some spin form manifold W. Or if you don't like spin, you can take a simply connected one with even intersection form, and you can glue that on. So you always know those exist for any integral homology sphere. You can glue that W on. And now you have a closed form manifold. And because of how you chose W and how you chose this F sub W, you in fact know that F together with F sub W is a characteristic surface inside of this now closed form manifold. So now with that all set up, we're ready for the proof. You apply this closed formula that we started the talk with, and then you'll use, so that closed formula involves the Arf invariant of this now whole surface here, and that Arf invariant can be split by the additivity of the Arf invariant, actually. So you get the Arf invariant of this 1/2, this F sub W, and the Arf invariant of F. Sigma of this whole form manifold can be computed again by additivity, so-called Novakov additivity. It can be computed as the signature of X and the signature of W. And the signature of W, well, divided by 8, that's going to contribute this mu term. And we'd have to look at the self-intersection of this whole surface here. But in fact, its self-intersection is just equal to the self-intersection of F. So one way to see that is to just change this surface a little bit while preserving its homology class. Namely, you can take a Seifert surface in this boundary of X again, and you can just add that Seifert surface twice to this guy and split it into two connected surfaces. So the F capped off and the green stuff capped off. And the green stuff capped off is all going to just live in sigma cross I. And so there's no interesting self-intersections that can happen there. So that all just goes away. And it turns out when you cap off F in this way and look at the self-intersection number, you just get the self-intersection number of F that you started with. And so the last piece of this is identifying, using the additivity of the Arf invariant. You have these two Arf invariants, the green and the red. And by this preceding 3-dimensional, 4-dimensional bridge lemma that I mentioned before, the Arf invariant of the green stuff is in fact just the Arf invariant of its boundary. So there you have it. And if you want the topological version, you just look at some, it follows very formally. You just look at some properties of the Kirby-Ziemann invariant. For example, it's concordance invariant. And it follows from the smooth case fairly readily. So that's this formula here. I'd like to mention just how this H1 condition can be defined away, so called defined away. So you start in the closed setting. You can prove the same closed formula of Rocklin by just erasing the H1 condition. The only difficulty is defining the Arf invariant of your surface. And what you do is you can just choose any, you can do surgery on your form manifold to get to a form manifold that has 0 first homology. And you can compute the Arf invariant of the surface. So you can do that surgery away from the surface and just compute the Arf invariant there. And you can declare that to be the Arf invariant of your original surface. And it's in fact well-defined independent of how you do the surgery. If you look back at this formula, you'll see all the other things are concordance invariants or won't be affected. And so with that definition, you can then erase the H1 condition and the same formula holds. And this again holds for this theorem that I just wrote down. So you can erase the H1 condition, but you first prove it with the H1 condition. That allows you to define it, define the important Arf invariant of the surface without the H1 condition and show it's well defined. And then the theorem follows immediately without the H1 condition. And I should mention that an alternative proof of this whole thing can be given in terms of spin structures. And the idea there is that when you're a characteristic surface, that means that, in fact, that being a characteristic surface is equivalent to the fact that there's a spin structure on your complement that doesn't extend across the characteristic surface. And so there's a construction that takes this spin structure on the complement and actually induces a spin structure on the characteristic surface. And then if you know about spin structures on surfaces, there's an Arf invariant there, and that's the same Arf invariant we've been seeing here. So all these things have analogous definitions, and this wasn't showing up for us because in integral homology spheres, there's unique choices of spin structures, and so we didn't have to worry about this just yet. Or for example, in the four manifold, there's no first homology, so there's a unique spin structure on the complement. So these didn't show up, but they'll show up a little bit later on. Okay, so now I'm going to briefly discuss some generalizations of all of this. So the first generalization to make is the case where the boundary is a link instead of a knot, and this leads to this notion of properness of links. So let me repeat the process from before, going back through the algebra. So here, let's just start from the beginning again. You have your same finite dimensional Z2 vector space V, and you have a now symmetric bilinear form that isn't assumed to be non-degenerate. You'll see where these show up for links in a second. You then have the radical of this bilinear form. These are the set of vectors that pair with all other vectors to give you 0. And you can again look for quadratic refinements of your bilinear form, and you call one of these proper if it totally vanishes on the radical. That's what it means for such a quadratic refinement to be proper. And in this case, and only in this case, can you define the Arf invariant. Namely, you can quotient out by the radical and make sense of Q still, and you can take the Arf invariant of that, and that will give you an Arf invariant in this setting. And this leads to an Arf invariant of links. So in the link setup, we again take any bounding Seifert surface S, and this H1 of S is again our vector space V, but now there's a radical we have to deal with. In the last, in the case of knots, there's no radical, but here you have the image of the boundary H1. So for a knot, there's nothing, because the boundary bounds the whole surface and is therefore 0 in homology. But here you'll have a non-trivial radical. And so when you write down the same Q sub S as before for the case of knots, you find that this is proper if and only if your link satisfies the condition, which is also called the link being proper. So that's this kind of funny condition on linking numbers. So you need every component of your link. When you look at its linking number with all the other components, it has to be 0 mod 2. So it's a kind of funny condition when you first see it, but it shows up inevitably throughout all of this. And it shows up, here I'm showing you how it shows up through just the algebra perspective. It also will show up from the spin structure and the pin structure perspective. So it's kind of, can't get around it. Yeah, that's this slide here. I'm just mentioning that this properness is also coming up from the spin perspective. And just to briefly say that how that happens. So in the spin perspective, in the old case, what you can do to compute your Arf invariant of your knot is you can take this surface again in sigma cross I. There's a unique spin structure on the complement of it that doesn't extend across it, and that induces a spin structure on this surface F. And that surface will have the bounding spin structure on its boundary. So you can just cap it off. And then you have a closed surface with a spin structure, which has an Arf invariant. And that Arf invariant is the Arf invariant of K. That's another way of computing it. And when you didn't have K, but you instead had an L here, you do the same thing. There will be a unique spin structure on the complement of your surface. But the only way that when you then induce a spin structure on this surface, the only way it's on the boundary is always the bounding spin structure, is if you started with a proper link. So that's just for those familiar with spin structures, that's how this shows up in that context. Therefore, you only get the Arf invariant of a link when the link is proper. And in this case, the previous theorem holds and the proof is very much analogous, or you could prove it using spin structures also. So what about the case when F is no longer orientable? So here, I'm just flashing some invariants at you again before explaining what they are. So here is the theorem that you can prove in this case. So you have this F in X. F is characteristic, but no longer orientable. X is still oriented and compact. And this should say boundary of X is an integral homology sphere, and the boundary of F is a proper link. Then you can prove this formula here. So now it's a mod 16 thing, but this reduces to the previous theorem when you take F to be orientable. I see, and this should also, this boundary F here should also be a boundary of X. Sorry, it's mu of boundary of X. But there's this new invariant beta, and it's called the Brown invariant. Instead of the Arf invariants from before, you have this so-called Brown invariant. And we need the Brown invariant of a proper link in an integral homology sphere, and the Brown invariant of a characteristic surface with proper boundary in such a form manifold. So I'm going to just briefly discuss what those are here. So this is just the discussion of the Brown invariant. In my head, this is just the Arf invariant when you have non-orientable surfaces. This is what leads you to thinking about Brown invariants. So the setup I'll just go through very briefly. You have a finite dimensional Z2 vector space, a symmetric bilinear form, and we now talk about enhancements to this bilinear form. So you should maybe think V is H1 of RP2, and then you won't have any quadratic enhancements as we had before, but you will have these new kinds of enhancements. So these are Z4 valued functions on your vector space that satisfy this condition here. So if you were in our old case, you can get these enhancements by just taking Z2 to be sitting inside of Z4. And then you'll again, that's one source of enhancements, but when you aren't orientable, those won't exist, and you'll have these other enhancements. And when E is proper, so when it vanishes on the radical, then you get this so-called Brown invariant, which is a Z8 valued invariant. Now it's possible to get very confused about powers of 2. So E is Z4 valued, V is a Z2 valued vector space, and beta, a Z2 vector space, and beta is a Z8 valued thing. And then our congruence will be Z mod 16. So you can apply this. I'm sorry. This is how you actually define the Brown invariant. This is a sort of democratic method. So you take each of these values, 0, 1, 2, and 3, and I'm going to let E sub I be the number of times E takes on one of those values. And then you have these this chart. So you look at the sign of E0 minus E2 and the sign of E1 minus E3. And it turns out that they'll never both be 0. So you'll never end up in the middle here. This is like with the Arf invariant, they'll never be equal. And then you look on this chart. So if E0 minus E2 is positive and E1 minus E3 is negative, then you end up with this with 7. 7 will then be your Brown invariant. So you get this Z8 valued Brown invariant. And this, in fact, similarly, on just a level of algebra, this classifies quadratic these enhancements of your form, not quadratic anymore, but these Z4 valued enhancements are classified by this Brown invariant. And now you can apply the Brown invariant to links. You'll need a proper link in a homology sphere. And you can define the Brown invariant as a Z8 valued invariant. And what you do is you again choose a bounding surface. It doesn't need to be a Seifert surface anymore. Doesn't need to be orientable. And here's your enhancement. You take homology class X and you realize it by an embedded curve on your surface, and you count the number of half twists in the neighborhood of that surface. And that gives you something in Z mod 4. And then you take its Brown. It turns out that this is an enhancement of the intersection form. You take its Brown invariant, and that's the Brown invariant of the surface. And the Brown invariant of the link, you have to make up for this choice of Seifert surface by taking the Brown invariant of the surface and subtracting off the sum of the framings of the components of L induced by this Seifert surface. And in fact, this invariant has a nice relationship. So in the case of a link, I didn't mention this, but to take the Arf invariant of a link, you need to orient your link. And it doesn't matter if you reverse all of the orientations of your components, but if you just change one orientation of one component, it's a little bit erratic. And exactly how erratic it is this formula here. So if you choose a orientation for L, this is this relationship between the Brown invariant and the Arf invariant, and tells you how the Arf invariant changes if you change single orientations of your components. Okay, and then similarly, in the case of characteristic surfaces, you can do this same deal. You have a non-orientable characteristic surface now, and you can define an enhancement. And it's similar to the old definition. I'm not going to spend too much time on it, but you take a curve on your surface, you have it bound this should be a partial of D here. And then you look at how D intersects F, and you also have to account for the twisting, which will be a Z4 factor of D. And you get this enhancement, and it's an enhancement of the intersection form. And in the closed case, there's a theorem of Gallot and Manin that was extended to the case of topological manifolds by Kirby and Taylor. That's a generalization of this theorem of Rocklin to the non-orientable case. So here you take F not necessarily orientable, X is again oriented, and F is still characteristic, and everything is closed here. And then you have this formula that it recovers the old formula, Rocklin's formula. If you took F to be actually oriented, then this E will be twice the Q from before. And so this recovers and extends the old formula. And we can apply this and a similar proof strategy to obtain this generalization. So this is a theorem of mine for the characteristic surface no longer necessarily oriented, and its boundary no longer needs to be a link. Sorry, this should be beta of not C, but beta of boundary of F, of course. And this recovers the old formula if F were in fact orientable. So I'm not going to dwell on this, and it's not important to remember what the formula looks like or anything, but that's what it is. And this can also be proven using pin minus structures and this isomorphism between Z mod 8 and the pin minus structures up to cobordism on the surface. It's very similar to the spin proof. In fact, this is how these beta invariants were originally defined, using these pin minus structures, and this combinatorial interpretation of them is another thing that's novel to this paper. And then you can ask to drop the condition that the boundary of X be an integral homology sphere. And this part gets rather complicated. I'm not going to even state this theorem. I'm just going to give you a feeling for it. So X is now compact, and all these previous theorems would have worked if the boundary of X were no longer connected. There would just be some sums over boundary components. So I've bothered to write that down precisely here. So you have a characteristic surface, not necessarily connected or anything, not necessarily orientable, and its boundary is always proper where it meets the boundary of X. And you have some auxiliary data here. This is a choice of spin structure on all of the boundary 3 manifolds, choice of pin minus structure on the complement of F, and a choice of longitudes of all of the boundary components of F in the boundary of X. And this allows you to define these invariants here, these betas, which are fairly complicated. This is due to Kirby and Taylor, this definition of these betas. You can also define beta of your surface, and you get this very general formula that, if you like, is a kind of combinatorial definition of the Kirby-Siebmann invariant for compact four manifolds now, compact orientable four manifolds. So it's not important to understand this formula at all, but the proof is roughly the same once you have all the definitions, relevant definitions in place. And here, this is these Rocklin invariants of M together with spin structures. And that's it. So thank you very much for having me. I hope this was somehow helpful. Thanks.